Hi, welcome back to our last chapter, chapter 11. In this section, the first section, we're going to take a look at something called goodness of fit. We'll take a look at contingency tables in 11 too. But in section 11.1, we're going to take a look at something called goodness of fit. All right, now this is a pretty straightforward concept, but the words don't make sense sometimes. So our key ideas is we're going to take a look at the goodness of fit. And what we mean by that is we're going to take a look at, instead of a binomial experiment, we're going to take a look at a multinomial experiment. And we are going to see that if the data that we gather when we run the experiment matches some preconceived notion about this. Now, if you remember, these guys, binomials, every time you asked the question, every time you ran the trial, every time you did the thing that you were doing, there were only two outcomes. We call them success and failure. In a multinomial experiment, every time you run the experiment, there's multiple outcomes. Okay? So imagine that the experiment is to reach into a bag of M&Ms, pick out an M&M, and then the experiment is, what color is that M&M? So there isn't success and failure now. There's just outcomes, and there's a bunch of them. There is an outcome for every color M&M. Now, what goodness of fit testing does is, before you run the experiment, before you count your M&Ms, you say, I expect to see this many of this color and this many of this color and this many of this color, and so on. You run the experiment, and then you see if the data that you collected matches what your expectation was. Now, the fancy way to say that is we have sample data consisting of observed frequency counts arranged in a single roller column called a one-way frequency table. Okay? And then we are going to test to see whether it agrees with some particular distribution. Okay? We will hypothesis test the claim here being the distribution and how in this case, the colors of the M&Ms are supposed to be distributed. And we see if the observed agrees with the claim or the expected. Okay? So by definition, a goodness of fit test is a test that is used to test the hypothesis that the observed frequency distribution matches some claimed distribution. There's lots of notation we're going to use here. We're going to use the capital letter O to stand for the observed frequencies for the outcomes. Okay? We're going to use the capital letter E to represent the expected frequencies for the outcomes. Okay? K is going to represent the different categories of cells, or specifically, K is going to represent the number of possible outcomes. So if your experiment has 7 outcomes, 7 possible outcomes, K would be 7. Right? N is going to represent the total number of trials. Right? How many times did you run the experiment? And then we are going to have this P that's going to show up, a lowercase p, that would represent the probability of falling into a particular category. Right? Now, along with these Ks and along with these Ps, we're sometimes going to see subscript notation. Like K sub 1 would represent the first possible outcome, K sub 2, K sub 3, K sub 4, and so on. Right? We also might have P sub 1s to represent the probability of K sub 1 occurring. We're going to have a P sub 2, which would be the probability of outcome 2, K sub 2 occurring. P sub 3, and so on and so forth. Right? So while K represents the number of possible outcomes, K1 would be the outcomes for the first, outcomes for the second, K2, K3, and so on and so forth. So what we're looking at here is, by definition, a multinomial experiment because for each individual trial, there is a more than 2 possible outcomes. So essentially, it's binomial if it's 2. It's multinomial if it's more than 2. What does more than 2 mean? 3 or more. There's no limit. You could have some silly multinomial experiment with 500 possible outcomes. That's more than 2. Multinomial. Okay? The requirement is, though, that the probability for each outcome is fixed. That is, the probability for outcome 1 is a fixed value. Probability for outcome 2 is a fixed value. Just like with binomials, the probabilities don't change no matter whether you're doing the first run of the experiment or the second or the third. Right? Our observed frequencies, or O, are going to be the data that we see when we run the experiment. So the observed frequency is the frequency for the categories when you run the experiment. Okay? These will be given in the setup for the problem. Sometimes they're given as a data set, or sometimes a table, sometimes a graph, and we got to pull them out and figure out how they work. Right? Our expected frequency, E, is going to be the claim of how the outcome should be distributed. Right? It is a calculated frequency for each category. So if I had a multinomial experiment that had 3 outcomes and I thought they were all the same, then the expected frequency for each outcome would be 1/3, 1/3, 1/3. And if I ran the experiment 30 times, I would expect to get 10 in each. 1/3 of 30 is 10. Right? So the expected frequencies are found. The expected, undo that, wrong marker. The expected frequencies for each category, E sub I, so like E sub 1 is the expected for the first category. E sub 2 would be the expected for the second category. They're always found by taking n times P sub I, where this n is the same as the n back up here. So that n's the same as that n up there. It is the number of trials of the experiment. And that P sub I is the P sub I we talked about. It is the probability for each of those individual category outcomes. Right? In general, the expected frequencies are our hypothesized distribution. The expected frequencies are what the claim is going to represent. It's the, hey, here's what we believe should happen. Let's see if our data matches what we believe should happen. Right? The requirements to run one of these tests are, of course, as always, your data is supposed to be random. Right? The sample data consists of frequency counts for each category, and the experiment has to be big enough. That is, the expected frequency for each category has to be 5. Not the observed frequency, the expected, right? If I expect to see at least 5 of each color of M&M, then I've got a big enough experiment that I can run a goodness of fit test. Okay? When we talk about the null and the alternative hypotheses, the null is always going to be that the frequency counts, the observed frequencies, match the expected frequencies, that the O matches the E, that the observed that we saw matches the E. Okay? The alternate hypothesis is that they don't, or that more simply, O does not equal E. So that's going to be the hypotheses never change for this. It's always O equals E and O doesn't equal E. Right? Now the math that's behind the scenes is this right here, right? That thing right there is the Greek letter chi. It's squared, so this is called a chi-squared test. That's the test we're going to run, a chi-squared. I know it looks like chi, like the T, but it's chi. Right? The math behind the scenes is this mess over here, right? So when I take a look at this mess, I'm looking here in the numerator. The observed minus the expected, that's going to be squared. We divide that by E, and then we take the sum. Right? So for every individual category, for category 1, we take the observed for 1 minus the expected for 1, square that, and then we take the observed for 2 minus the expected for 2, and then square that, and we take the observed for 3 minus the expected for 3, and square that. At each stage, we're dividing by e. So if I were to write this thing out, it's going to look like, what is that going to be? O1 minus E1 squared divided by E1 plus O2 minus E2 squared divided by E2, and so on and so forth as we march on through there. Right? We're going to add all those up, and what ends up happening is, if these two things at every stage are close together, if the observed is close to the expected, that yellow highlight there in the parentheses is going to be a really small number. And then the sum of this will be a really small number. Right? If those two things are far apart, then that numerator is going to be a big number. And so when we run the test, it's running on a chi-squared graph, which is this weird graph that you're seeing here in front of you. It's got a skew to the right, starts low, goes up, comes down, and skews way out, right? And we're over here on this left side when O's and E's are close together. We're over here when O's and E's are far apart. So this is when they're close, or when the observed matches the expected, and this is when they're far apart. When the observed doesn't match the expected. If we're over here on the left, where the observed matches the expected, we don't reject the null hypothesis. So if we're over here, we don't reject. If we're over here, then we do reject. So when the chi-squared is a big difference, we reject. Right? If we fail to reject, then our argument is that we've got a good fit with the assumed distribution with the expected values. If we do reject, then we say we don't have a good fit. Okay. All right, let's take a look at one. From start to finish, we'll see if we can make this work. A researcher claimed that the number of different colored candies in a bag of dark chocolate M&Ms is uniformly distributed. All right, so I'm going to stop right there because we've got a claim. The claim that the number or the frequency of the colored candies is uniformly distributed. What does uniformly distributed? Well, uniformly distributed, that means they are all the same. What do I mean by all the same? It means that all the colors, the brown, the yellow, the red, the blue, the orange, and the green, should all show up with the exact same frequency. That's what uniformly distributed means. Uniformly distributed means the expected frequencies should all be the same. Okay? All right, I'm going to keep reading now. To test this claim, you randomly select a bag that contains 500 dark chocolate M&M candies. That means our N, the total number of trials of the experiment, is going to be 500. So I know you're thinking, wait, what's the experiment here? The experiment is, what's the color of a candy? And how many candies did we test? We tested 500 candies. Okay. Results are in the table below. At a significance level of 0.1, perform a chi-square goodness of fit test to test the claimed or expected distribution. So now I got a table here. These guys, the brown, the yellow, the red, the blue, the orange, the green, the colors are going to be our, what were those again? Oh, those are the different possible outcomes. Those are the Ks. So it looks like we have K equals 1, 2, 3, 4, 5, 6 of these. K is 6. We have 6 different possible outcomes. Right? Our numbers over here, the 80, the 95, the 88, the 83, the 76, and the 88, those are all of the individual frequencies for each category. So really, that column should be labeled observed frequencies because that's what we literally observed. Right. Now, what we need to make this work is we need to know what are the expected frequencies. So actually I put this green right here in a bad place, so I'm going to erase it because we need to create another column over here that's going to have our expected in it. Right? Now, how do I get my expected frequencies? What is the expected number of brown? Well, if there's 6 categories, I should expect brown to be 1/6 of the total number of M&Ms if I'm uniformly distributed. So I should expect this to be 500 divided by 6 because there's 500 M&Ms. 1/6 of them should be brown, so it should be 500 over 6. In fact, since this is uniformly distributed, every single one of these should be 506 because they're all the same based on the claim that has been made. So those are my expected values, or my expected frequencies. So our claim is that the color distribution is uniform. Our hypotheses are that the observed matches the expected. Our alternate is observed doesn't match the expected. Okay. Those two hypotheses, this null and this alternate, are always going to be this for these problems. That's just how it is. Okay. Our data for this is the table above and our alpha level of 0.10. Okay? Now what we need to do is we need to run the proper test. But before I can run the proper test, I need to get my calculator up. So I'll be right back. Okay, I got the calculator up and now I need to run the proper test here. So if I go to stats and over to test, I'm looking for a chi-squared goodness of fit test. There it is right there. Okay? So I'm gonna press enter. Uh-oh. Oh, okay. All right, so see what it's asking for? It's asking for the observed and it's asking for the expected, and it wants those in lists. So that means that we've got to put the observed from somewhere, and I'm going to put the observed in L1, and I'm going to put the expected in L2. Okay, so I need to go back over to stat, to edit. I got some garbage in there from before, so I'll clear it out. Clear it out, and I'm going to put the observed in L1, so 80, 95, 88, 83, 76, and 78. Now I need to come over here, and in L2, I need to put the expected. 500, whoops, not times, divided by 6, and then I'll just continue that down. I'll be back when it's done. Okay, so I've got all that data in. The fact that those are decimals over there in L2 doesn't bother this. It can handle that. So now that I've got the observed in L1 and the expected in L2, I can run back over and run that test. So chi-squared goodness of fit, observed is in L1, expected is in L2. Degrees of freedom, what's that? Oh, unfortunately, this is one example of one test where we actually have to input the degrees of freedom. So our degrees of freedom is always going to be k minus 1. The number of classes minus 1. So for us, that's going to be 6 minus 1, which will be 5. And so I'll put 5 in. I'll go down to calculate, and I'll go ahead and calculate it. Now, that top thing up there, that weird looking thing right up here, that's our chi-squared test statistic. And we've got a p-value below it, where p is equal to 0.6975, right? Now that I've got a p-value, I can compare my p to my alpha. Here's my p, 0.7 roughly. Here's my alpha, 0.1. Since the p is way bigger than alpha, we are going to fail to reject the null hypothesis. Now, what was the claim? Well, the researcher claimed that the distribution was uniform, that the observed should match the expected. And if we fail to reject the null hypothesis and the claim is the null, we would say there, my pen stopped working again. Oh my gosh, this is a bad time for this too, because we're almost done with this example. We would say there is okay, I'm just going to say the words and then stop this video. There is not enough evidence to reject the claim that the colors of the M&M bag follow a uniform distribution. All right, I'm sorry my pen stopped working there. I'm going to have to restart my tablet again. I don't know why it does this sometimes. It's so frustrating. But anyway, I'll be back for part 2 of this video. Have a great day.